Ready to start recording? You already are, perhaps. You ready to go? Okay. Welcome to Python Epiphanies, PyCon 2018 here in Cleveland. You'll see here the survey link, the downloads for the slides, the handouts. The piece I quote in here, if your use of Python sometimes feel like an outsider, you feel like an outsider, that's sort of the feel of the kind of target audience I was trying to reach with this. And I think it's worked pretty well. I've taught this a number of times at PyCon and usually get good reviews. Well, always have gotten good reviews. I'm a software architect in Canada, largest mutual fund company in Canada, IGM Financial. I help quants with Python, is a lot of what I do. I've done a number of tutorials over the years at PyCon. This is my 12th PyCon. It sneaks up on you, and I think I've taught Python something in a tutorial 11 of those years, if you count this year. I do some Python workshops and coach at startups occasionally, remote or local, in Winnipeg, where I'm from right now. Asked you questions already, and so we'll move past that. Let me talk a little bit, and the first 10 minutes, 15 minutes are going to feel slow to some of you, maybe all of you, and just bear with me. Especially those of you who came from the languages, some of you raised hands. You're used to thinking about variables a certain way. Even if you learned Python as your first language, if you've read anything about computer science or you read blogs or whatever, you kind of, I suspect, have absorbed a meaning of variables that is, I think, unhelpful with Python. With Python, it works differently, and if you understand that, then a whole bunch of stuff becomes much clearer in Python, and that's the theme that I will use to teach you a bunch of intermediate moving towards advanced stuff in Python. To do that, I'm going to speak very slowly and carefully using terms that avoid the word variable, for example. So first 15 minutes, don't run out of the room yet. It'll go faster and be more interesting. So variables, in math, a variable is something that varies, like in algebra. In most programming languages, a variable is a box that gets allocated in memory. We think of it as a box. And what's in that box has a type that's defined as part of the compilation. And the type determines what machine codes are actually issued to work on the values in that box. And so, for example, if you look at this little piece of code, we've got something that does floating point arithmetic to return the square of something, and something that does integer. And if you compile those two, you actually see you get different instructions because it knows it's a float and it needs to issue a different instruction to do floating point multiplication than it does integer multiplication. Python's not like that. So this is the way most programming languages that get compiled, statically typed and compiled, work, not Python. When you do an assignment in most programming languages, you're actually changing the value of what's in that memory location. You're overriding those bits with different bits. That's not what happens in Python. And aliases, two names for the same location of memory, are pretty rare. Python, variables are variables. They are values that vary over time, but they aren't the other stuff that most programming languages, they are in other programming languages. I'm going to use the word names and objects and binding, and I'm going to hope that you adopt at least some of that, or at least make sure you understand how to think about it that way. So I'm going to start by reviewing objects, how they're created, talk about names a lot, talk about all the ways that names and namespaces get changed in Python, and I'm going to use lots of introspection in several places, not ways you should be using it, but it'll be instructive, I hope. And I don't know that I'll quite finish it. I would love it if you interact with questions. Sometimes I'll say I'll answer that later, offline, like after the tutorial or during the break, or it's going to be answered later. But I want to hear the interruption anyway, because that gives me feedback in terms of how you're tracking what I'm trying to teach you. Any questions? Okay. Let's see if I can go the right way. I did. All right, so here's some boring foundational stuff. And again, I'm going to talk very slowly about this. Bear with me. So everything in Python is an object, at least at runtime. The creation of objects is unrelated to the names that are bound to those objects. Objects actually don't even know their names, with some exceptions, sort of, that I'll show you later. There's lots of ways to change namespaces. So first, let's just look and see what happens when we execute this line of code. We're at the REPL, or the equivalent, the read eval print loop. So when I hit enter, that single character, the digit 1, is going to be sent off to the Python interpreter. And the Python interpreter is going to try to interpret that code as it's going to try to parse it, compile it, turn it into bytecode, and execute it, right? So it sees that and goes, oh, that's an integer literal 1. It goes off, and in memory, it creates an object that represents an integer. And that object is much more than 64 bits. It's actually, we'll see how big it is later. And it has embedded in it, it knows the type, it knows, has references to its documentation, all sorts of stuff in that single object that is created when you just hit that one. And then, of course, we're in the read eval print loop, so when we hit enter, it's going to then display the value of that expression, which it won't do if you're running a program. And I'm going to get back a 1. Wasn't that boring? Really, but it's important to understand that that's what's happening when you're running these things in Python, right? So what else can we do? Well, we can create floats, and we can create string literals and lists. So here we've got, again, the 1 gets evaluated, creates an integer object 1. The 2, an integer object representing the number 2 is created, that somewhere inside it has a little box with a 2 in it. And then a list is created, and it has references to those objects. And we can create dictionaries. Every object has a single unique ID. In CPython, that's actually a memory address. That's not guaranteed to always be true, I don't think. Oh, in CPython, it probably will because extension libraries use it sometimes, I understand. Other versions of Python, other implementations of Python, it's not always the memory address. Every object has a number of attributes. So if we take, again, quote, string little quote, Python sees that, goes and creates a string object, a big thing in memory that has a little part of it which actually represents the string, the bytes. And then we access an attribute of it with a dot, and it's going to go look in the namespace that that object has, is sort of the way we talk about that. And we see what it is. Okay, it's some representation of that string, that upper function object, which actually isn't a function. It's interesting it shows it that way. But we can call it, and we get back a new string, right? So we didn't change the string literal. We returned a new string literal. Sorry, a new string object. We can look at all the attributes of an object by passing it to the function dir, and there are lots of dunder arguments. When you see underscore, underscore, add, underscore, underscore, we pronounce that dunder, as in double underscore. So lots of dunder attributes, a bunch of other attributes here, lots and lots of them. Every object has a single type in Python, and that type, as I said, is actually stored in the object itself. So the type of 3.14 is float. If you call type, it acts like a function, it's a callable, and it will tell you the type of an object. I can actually also go look and see that right there. There's a dunder class attribute on the object that got created there, the 3.14 object, and it shows us the float. Right, so you can see these various types. Types, subclass, other types. So I can use the inspect module, get the method resolution order, and see that 3.14's type is a subclass of object. Object's the top of the hierarchy for all classes in Python, for all objects in Python. You can see that that's actually stored in these dunder attributes, as is the method resolution order. Method resolution order, in case you don't know, Python, you can have multiple inheritance, so it has to figure out which order does it go looking for methods when it's looking up the chain. All right, so 1 equals 1, an integer object gets created, another one gets created, equality gets executed against them, or run, there's a function basically, and it's, why is this jumping around? Right, and the class of that result is bool, base class is int, base class of that is object, okay, and of course MRO or inspect is a better way to do it. So we can see that true and false are objects, instances of the bool class, which is a subclass of int, which is a subclass of object. Okay. A bunch of objects actually exist at startup. We don't have to create them with literals. things like true. So there's the name true is there, and it's got, when we access, so again, the name true. So actually, when I hit true, type in true, Python doesn't go create an object based on that, or maybe it does, but no, can't think of any case it would. It actually sees that name and says, well, that looks like an identifier. I'll go look it up and return the object that that name is bound to or that that name references. Right? And so we can look at this true object, and it's got a class. Bool is a name that you can access. Right? So true's class is the same as the class of, like obviously they're the same class. Two ways to get the true object. One is to use its name. One is to say 1 equal 1, and you get back the true object. The object that represents true. ID, so the ID of true's class, this should be, so I'm going to show both of these IDs, and we see, yeah, they're the same address. And obviously they're equal, but not only are they equal, but they are the same object. Right? So equals for equality is for object identity. And what does it mean, object identity? If I have an object, of course it's identical to itself. So when we say it's for object identity, it's if we have two names for it or two ways to get a reference to that object, are these references to the same object? That's really what identity is about. Okay, built-in, bunch of built-in types with names. So for example, float. Yeah, we saw that one already. And you can see that the class attribute and the float name refer to the same object. This is the right way to check to see if a class is something, though. Is 3.14 an instance of float? The reason that's better is you might want to let someone pass you something that's not a float, but is a subclass of float, and you still want your code to work if you have to check types. We can look at float MRO, okay. What's the type of a type? Well, it's type. Sorry for the confusion when I speak that out loud, but float's class is type, and its class is type, right? So a float type is a subclass of type, which is a subclass of object. We'll see type later. Of course, if you just keep going, it's just a little loop there. There's some built-in functions. Here's one, len. It's got a type, which this one is built-in function or method. It's got an MRO, which is pretty simple. It's just a subclass of object. So for review, everything's an object. Every object has a value, a type, base classes, a unique ID, and attributes. We can also call other objects. So I'll call objects when they're callable. So let's look at a couple things here. If we do import sys and do a get ref count on it, sys get ref count. So I said that objects don't know their own names. Objects do. Let me rephrase that. Objects don't know their own names. The system, Python runtime system, remembers how many names have been bound to an object by counting. And that reference counting is stored in the object because that's the most convenient place to do so. So I can ask Python, what's the reference count of 3.14? And it's 3. Interesting, it's 3. Why do you think it's 3 instead of 1? You'll explore that a little bit later. True, so the name true, so I'm running Python interpreter, Jupyter notebook kernel, and in that, all those layers that are running there, the name true exists in code that's loaded in memory 3,000 times. Okay, so that name true has been, there are 3,000 of those names in the system, in memory, referencing that single object. None's a much more popular one with 24,000. How about object? You think it's going to be even more? You would think, but there aren't that many names that reference the actual object. There's lots of indirect references to it, but names that exist in memory that are referring to the top of that hierarchy, there's a lot less than there are for the word none, than the name none. Okay, so all these expressions I've been typing, like len, what does it return? An object. Callable len. Len is a name, dereference it to an object. It's bound to an object. The object reference is sent off to the whatever callable resolves to, right? So callable is a name of an object. This object is sent off to that object by passing the memory address behind the scenes, and that thing returns something. Well, what does it return? An object. right? Call this function, what gets returned? An object. That's an object. Method wrapper len is an object, right? Everything in Python is an object at runtime. Some of these objects are callable, like int. You can check by calling the callable callable. Callable means it works a lot like a function, but there are other things in Python that are callables. What else do you call? Name, open paren, and then some arguments and close paren. What's that? Classes, yeah, you instantiate classes. So classes are callable. And so type, for example, is a function. Well, it's also a class. So it's used interchangeably, even in the Python documentation. It's yeah, call the type function. Well, it's actually a class, but it doesn't matter. It's behaving like a function. It's a callable. So the notion of callable, and there are others, actually, I'll show you one later. Callable is a more general thing than just a function. A function has a more precise definition. All right, so let's call that. If I call int with no arguments, so int is a class, but I'm calling it, and it's kind of acting like a function converting 3.14, or it's acting like a class. They're interchangeable in this case. All right, dict, if I call, so all of these, most classes, if you call them with no arguments or instantiate them with no arguments, they return kind of a base case, like an empty dictionary, etc. True is not callable, so if I try to call it, I will get an error, which is it's not callable. But if I call it with no arguments, the bool class or type, I get false. 3.14 is a float. It's got a bunch of attributes, including these interesting ones, conjugate, as, interratio, hex, imag, real. The imaginary and real, that's because complex is actually a type in Python. So that's part of what you're seeing there. All right, so this is a method wrapper. It is callable. So 3.14 has a Dunderdict method. It's a method wrapper add of float object. And this here, that's probably I'm sure it is, the address of the object that got created here. So I can call it. So let's try calling it. Oh, expected one argument got 0. So that works, right? So Dunderdict is a method on float. You call a method by passing a set of arguments, and then it uses the object on which it's called as one of the implicit arguments. That's self when you write it that way, when you write a method. 2.add, oh, that's kind of cool. Syntax error. If you put parentheses around it, we fix that. Oh, that's interesting. You can't add 2 to 3.14? Well, you can, but it actually happens the other way. So Python, there's an add and radd methods, and so it doesn't force you to create both sides. It'll say, well, if I can't add it, I'll try the radd the other way. So that's why that shows up. All right, so what I will do throughout this tutorial, I forgot to tell you the pattern I'm going to do, which is I'll start by showing you a bunch of stuff, and then I'll give you a couple minutes, and usually it's between 1 and 5. It's pretty short, and let you do some exercises. I strongly encourage you when you're doing these exercises, don't just hit enter. Right? Look at this and say, okay, what's that going to do? What do I think it's going to get? Slow down, take some time, think about it, and they get a lot harder later. I guarantee no one's going to get them all right. Well, if you do, I want to hear it afterwards, if you actually predicted accurately what every single thing is going to do. And there are errors in here on purpose. So when you hit enter, shift enter, and you get an error, or however you're doing it, it's because I planned it that way, and I want you to learn from the error. So read the error message and think about, okay, yeah, what's going on here? And then I will usually stop you when about maybe a third of you are done, or half of you are done, and we'll move on. And those of you who didn't finish, don't feel bad. This is normal. I'm doing it. Some people are faster than others. Some people are using Python longer than others. So I'm not going to wait for everyone to finish, but then I'll go through it, and we'll go through it together, and I'll explain any things and answer any questions. Okay, so go ahead and take a couple minutes and run the first 5 really complicated exercises. So about 1 more minute, I'm giving you extra time on this one just to make sure everyone's up to speed with running the code. How many have finished? Okay, it looks like about 2/3, so I'll move on. Okay, so what do we learn here? Well, the size of a single string, you'd think that would take like 1 byte. It's actually 50 bytes long. And if you have a string of 3, it's 53 bytes. So it looks like the string is actually being stored in the object itself. We can infer from that. And those other 50 bytes, well, it's all those attributes and other stuff that are, some of the attributes are probably stored in it. Many of them are, or they're references to other things. Let's get the size of, okay, just exploring a few things there. There was a question back here, which is this sort of behind the scenes what Python's doing? And the answer is sort of. I would say this is behind the scenes how you could change the way Python does what it does. So, and I'll show you some examples later where we disassemble the code into bytecode. So if you define a Dunderdict method on an object, then when Python sees a plus, it will call your method. But it doesn't mean that Python's always calling that method, because there are more efficient ways for Python to do that addition, which is to go straight to the bytecode. Other questions? Okay. All right, so here's the second part where I'm going to slow down and try to make you think and talk about this a certain way. So names are really fundamental in Python. Almost every object is known by 1 or more names. Those names live in 1 or more namespaces, right? We saw how many nuns are there? 3,000, I think I said, in mine right now. So there are 3,000 namespaces where the nun object, where the nun name exists, and it's bound to that single object. Namespaces are very much like dictionaries, key-value pairs. They are bound, names are bound to objects, they're references. A name, another way to think about it, is it's like a post-it you put on an object, right? So I have multiple names. My kids call me Dad, so just imagine a post-it that says Dad, and stick it right on this object. I'm called Stuart, you stick it right on there, right? So I've got 2 names at least, and those are like post-its on an object. There's another way to think about it. Hadley Wickham, the way he says it is a name has an object doesn't have a name, and this diagram might help you think about it, right? So the name refers to the object, not vice versa. Objects don't know their own names, okay? So if we want to see what the names are in the current namespace, well, I'm running IPython in Jupyter Notebook, and there's a lot of junk. And so I'm going to instead do this. And then what that's going to show is basically, in my current namespace, it's got 3 columns, and it's empty. There are no rows right now. Name, value, and the address it's at. So let's start by number underscore 1. So Python sees number underscore 1. It says, that's a valid identifier. It's not a string literal. It's not a float literal. So I'm going to look it up in the current namespace. It can't find it. So it's going to give me a name error. Number 1 is not defined. All right, so now, this line right here, you could say I'm assigning number 1 the integer 300, but I don't want you to think that. What I want you to know when you say it that way is maybe what I would say, in this tutorial at least, is Python sees the integer literal 300, it evaluates it, creates an integer object which represents the integer object 300. It then looks at the number 1, sees the equal sign, says, oh, this is a name assignment, or it's at least an assignment. Number 1 on the left looks like a name, so I'm going to go look in the current namespace and try to find that name. And if I can't, I'll add a name to the namespace, key value pair in the dictionary. I will add that key to the dictionary, which is the namespace. I will then bind that name to that object by making the value in that mapping be the object that just got created. Well, that's why we say the shorter version, right? But that's all the stuff that's going on, and that you need to. I want you by the end of this tutorial to know when you see that. Oh yeah, all those things happen. All right. So when we do that, whew, a lot of stuff happened, and now we've got number 1, value 300, and it's at a particular memory location. Right. So a simple name statement, a simple name assignment, sorry, is not an operation on an object. I did not take a chunk of memory that already existed and overwrite it with something new. I went and created a brand new object out there in memory. I allocated a new piece of memory and put some stuff in it and then referred to it with the name. Okay? I think that's almost the only time, I think that's almost the last time I'll go that slow. Okay, so now if I try to access number one, I don't get a namespace error, a name error. Instead, Python sees that, looks up the name, finds it, and returns an object which it was bound to, is bound to, and then it shows me the value of that expression. That was a lot shorter, don't laugh. Oh, it's bound to, yes, yes. Okay. Okay, so Python does have variables in mathematical set. I said this already, so I'll let you read it if you want to. All right, so what happens in this case? Number one is already a name in the current namespace, so Python sees it and says, oh, well, the code is saying to bind this name to that object instead, and so it will shift it, right? Just imagine a pointer. It's pointing to the object 300. Now the name number one is going to point to a different object out in memory, okay? All right. And this is just in case you want to read it later if you're not catching what I'm saying. It's roughly the same thing. So let's see what's in memory. Oh, okay, so I've got a different value and different ID. 48. Yeah, different ID, okay. I don't know if it'll be a different ID or not, because all that Python guarantees is it's going to be a unique ID. Number two equal number one. Number one. You can ignore that comment. It's one of the few to-dos that I forgot to get rid of. Number one is looked up, and that object is then bound to number two. So if number two name is bound to the same thing that number one was bound to, right? Well, then number two, yeah, I can access it. I can access it. And we can see that they are the same object because their IDs are the same. That's what object identity means. They have the same ID. And because IDs are unique, it means they're the same object. Right? So I can ask not only the question, what are their IDs, but I can say, are they the same? Do those two names refer to the same object? All right. So del number two is a namespace operation. It's not going to delete the object. It's going to delete the name from the namespace. All right. So number two was a reference to some object out there in memory. Did the object get deleted? We don't know. Well, in this case, we do know because there's another name still bound to it. But in the general case, when you do del and delete the name, you don't know when Python, you can't guarantee when Python is going to clean up an object if it can. Sometimes you know, like in this case, it can't. We know it can't because there's still number one is a name to it. So names, it's when the last name is removed from an object, when all the post-its are gone, then Python can take that object, throw it away, and reuse the memory for something else. Okay? And now you can see we get the name error. So objects have types, names don't, right? So what's the type of number one? What you mean when you say that is, what's the type of the object that number one is bound to, okay? And so we can ask that question. What is the type of the object that number one is bound to? Oh, it's of type int. What is the type of the object that number one is bound to? Oh, it's of type string, right? So those of you who learned with C++ or Java, you can't do this. Python, it's trivial because it's not a box and the type is not stored with the name, the type is stored with the object, okay? So that's why the answer, I asked the same question at cell 105 and 107, got different answers because the name had been rebound to a different object. All right, so I can look at number one. Yep, and its value changed and its ID changed. I can get rid of that name from the namespace, and there's nothing left. So object attributes are also like dictionaries or like a namespace. So let's import the types module, just so we can get access to the types.simple namespace class and instantiate it. So I've got this reference to one of those objects now. That's what it shows up as. And it's got a Dunderdict, and it's empty. If I look do assignment here, I'm going to assign x1 and y2, i.e. I'm going to bind the x attribute of the p name, or the object that p refers to more precisely. I'm going to bind that to the object that gets created, which is the float 1.0, et cetera. So I've bound two names there. And now I look at the dictionary, and you can see that it really is just a dictionary. So I said names, a namespace is like a dictionary. Well, for an instance like this, it is a dictionary. It's exactly like a dictionary, well, almost exactly. There's, on classes, it's slightly different. And then I can, of course, access it that way. Right. So classes can define other methods to customize access on instances. We'll look at that. I think we're going to look at that now a little bit, yes. Right, so if I look at the dictionary here, I can see X and Y attributes, and I can check to see, give me the Z attribute, and I don't get a namespace error. I get an attribute error, slightly different than I would if it was a top-level name. But I can assign it, and then it'll work just fine. The set adder is a built-in function that lets you do the same thing, but with an arbitrary, like here, you pass in the object, which means you could pass in the object by name, so it could be a variable. And there's also a dunder set adder method that you can override to do that. It does exist on objects. And all of those are going to do the same thing. Z is going to have the 4. Del adder. What do you think del adder does? Does it delete the object? No, it's a namespace operation, right? So del adder just removes the name from the namespace. So it removes that key value pair, but the object might still be out there if there's some other name that refers to it. Same as del p.y. All right, assignment, access, and deletion of subscriptions are not namespace operations. They're requests to the object that you're calling the method on to do something, right? And here, those are calls to methods set item, del item, or get item, or at least you can think that if those exist. If not, then the operation happens lower, and I'll show you that in a moment. So I could say create a list, look at element 0, or I could equivalently say letters.dunderGetItem0, and it's going to do the same thing, which means you can write your own version of getItem, dunderGetItem, and change the way it behaves. So I said earlier, well, let me show you. I'm going to import the disassemble, the dis module, and I'm going to look at that. I hope I can fit these both on the screen. Right, so are they actually the same? And this gets back to the question earlier. And no, they're not. Load name, load const, call function, store name, load const, binary subscription. So in the first one we have at line 12, we have a binary subscription bytecode that actually gets executed. In the other case, we actually load the name, we load the attribute getItem, and whatever object it returns is assumed to be a callable, and we do a call on it, right? So if you've defined dunderGetItem on an object, it will get called instead, but if you don't, it'll just call the binary subscription. All right, let's do a few more of these. Right, so dunder set item. Here's a getItem with a subscription, a slice, sorry, which you can do by actually calling the slice built-in name that it refers to object directly, right? So when the 0:-1, Python sees that, it goes off and creates a slice object. You can create it directly with the slice built-in name. And then just, right, so again, 2 ways to do the same thing. Well, almost the same. I added the 2 so you could see it changed. In IPython, you can hit a question mark after a name. It'll give you help. So you can see slice takes a stop, or it takes a start and a stop, or a start and a stop and a step. Okay, let's look at this. I keep telling you that is for identity, equal is for equality. Let's just play around with that a little bit. So when I execute this, will I get true, 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 false, 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 or true, or false, true? Well, AB is equal to AB, so it's going to be true. What's the second one going to be? Is S and T, are they going to be bound to the same object? Who knows? You're wrong. You don't know. Who knows? Nobody knows. It depends on what Python does behind the scenes, would be my answer. So behind the scenes, Python is free to do what it wants. It doesn't, the contract that Python has with you on how it handles strings does not include this behavior. So you run different implementations of Python, you may get different behavior. In this case, true, true. What if we put a space between the A and the B and do the same, otherwise unchanged? True, false, all right? So there's proof you can't rely on is to mean it's really equal. That's not what it means. It means it is the same object, okay? How about integers? Similarly, you can't be guaranteed, right? And this one we'll explore a little bit later, I think very soon. And there's some explanation for why it's different, and I'll show you. Let's look at, just if you want to play around without going to look at the C code, right? Go ahead. Just go look at the C code, it's easier, but this is kind of fun. We can check in Python, see if we can find out, it's like looking for clues. Which integers in Python are pre-allocated for efficiency? And I can infer without looking at the C code that the answer is from -5 to 256, because the addresses are wildly different outside of that range. Okay? I can't guarantee that's what's going on, but you can figure it out just by looking at that, right? So by pre-allocating the integer 1, Python runs faster because there are so many names, so many references to it. It would use a lot of memory, for example, in the integer 0 and all those other ones. You can actually look at the difference between a couple of those memory locations. It'd be roughly the size of an int object rounded up to be aligned. How about that one? Okay. That one. Huh. Even if you do them on a different, same line versus different, what's different here? Oh, I did an I equals J equals 500. So I equals J equals 500 means I want both I and J to be references to a particular object. So there, that one you can guarantee that it's going to work that way in any implementation of Python. The first one you can't, because that's just putting them on the same line, multiple statements on the same line. All right, let's actually look and see what that turns into in terms of bytecode behind the scenes. Right, so we've got load const, and then we've got a dup top store name versus load const store name. Like it's doing, it basically is duplicating the top. Not meaning it duplicates it, creates a new integer 500, but it says, no, whatever's there, you got a reference to that integer, give me another reference to it, and both of them get stored. So you can see behind the scenes, it's just storing pointers. So why am I showing you bytecode? Why am I telling you all this stuff behind the scenes? I think if you want to work really well at any particular layer of abstraction, especially in technology, but probably in other things too, it really helps to understand at least some of what's going on underneath the lower layer, right? So we're sort of looking under there, looking under the hood or behind the curtain and trying to figure out what's going on, and that helps us make sure we have a more accurate mental model of how it's actually working, and then we don't get confused as much by why is Python doing it that way. Stuff starts to make more sense. That's been my experience, and hopefully will be yours. So exercise, take a few minutes and do some exercises. I had a question, which is, what is dis.dist actually doing? Well, what it does is it takes a string, hands it off to the part of Python that compiles the string into bytecode. But instead of executing that bytecode, it takes the bytecode and turns it back into a string representation of the bytecode that you can read. And so that's why it's disassembling, right? It's because Python is actually compiling and we're just uncompiling or disassembling it. This in the file, in the Python source code, in the Python subfolder, there's a ceval.c file, and this is actually the main loop of the bytecode virtual machine. Switch opcode, right? So if it's a no op, if it's a load fast, if it's a load const, well, all these names, store fast, these are now familiar to you because you've seen them for 30 seconds, right? Store fast, load name, pop top, dupe top, they're all in here. This is the C code that, as the bytecodes get executed, it runs and does the various things, calling out to other C functions to actually make the changes to do the execution. How many people are done with this? Good. Okay, so.
Can I ask you a question?
Question, yes.
For that one, when I changed the reference to 1, 2, 3, 4 versus 1, 2, 3, 4, 5, it came back still with the same reference as 3.
So you said you did that.
Took off the 5.
Sorry, that'll still work. And you got 3, yeah. And I expect that's gonna be true for any, so why is it 3? So do you think the object 1, 2, 3, 4, 5 exists before I hit that command, hit enter on there? Do you think some other part of the Python code has a name referencing that number? Because get ref count, what it's doing is it's basically taking the object, and asking Python, look in that object for where you happen to be storing the reference count. How many names are referring to that object? How many names are bound to that object? And return it so I can see it, right? So 1, 2, 3, 4, 5 very likely didn't exist in memory. Then I did this, and it did exist. And then I called get ref count, and it returned me a name with how many references there were. What's more interesting maybe is why is it 3 instead of 1 or none? Why is it not 0? Well, think about how get ref count is written. It's a function. It's got parameters. A reference to 1, 2, 3, 4, 5, that integer object was passed off as an argument to the ref count function, and then the function started executing, and it had a namespace. And in that namespace, it had to have a name for that object. So there's one of them. I don't know where the other 2 are. You got the answer? What? The underscore. Oh, there's another one. The underscore is, no, there's no underscore here. But I expected something like that. Is there some other name that gets created temporarily? There's another word. Anyway. Locals, I think locals is a function that will return a list of names, but I don't think it keeps it separate. It is, well, even so, there's no namespace here. 1, 2, 3, 4, 5 is just an integer literal. I've created no name in the current namespace referring to that 1, 2, 3, 4, 5. Okay. Okay. So you notice that I'm going to tease you like this all afternoon. Right, I'm going to say, I know, yeah, isn't this Darcy? Oh, no, I don't know the rest. But you can go find out. You had a question earlier, same thing I said, go find out, yeah. Anyway, okay, so 1, there's a whole bunch of 1s. So good thing they pre-allocated to me. 20 is a fair number. Object. None, we did these. Okay. What do you think this one's going to be? Interesting. Why is it less instead of more? So this one I understand. This one makes sense to me. The 1, 2, 3, 4, 5 I don't get. But this one makes sense to me because an object was created out there in memory of type object, so it doesn't have much. It has all the infrastructure for being an object and none of the behavior that is interesting at all. Except its ID is different than every other object in Python, which is why it's a good sentinel object. You need a sentinel object, one that tells you it's the end of something, and it has to be different from every other object. That's a way to do it. So I know that this name exists in the current namespace, and when this got called, a name in that function existed in that namespace, and it was, at that point at least, it was 2. One's the name in this namespace, and one's the name that it had while this function was running, because that function also needs a reference to that object, and it does so with a name. Okay? So, of course, this line's going to return false, because if I create a new object, it's going to be different than the last new object I created. So they're not the same object. Oh, sorry, that should be an is there. Is that true? I'm trying to think what the contract is between Python and the users in terms of creating an object instance on that class. It would be odd if it were true, and is was. It would be odd if that was. No, sorry, I'm getting confused. Never mind. This makes sense because 2 objects are only equal. So object defines equality B if it's the same object. That's what is going on here. Okay, any questions? Let's talk about functions. So what happens when you define a function? Well, what happens, functions and classes, by the way, is that this name gets put into 2 places. So the body of the function is evaluated, compiled, turned into bytecode, stored somewhere in an object. That function object is then bound to the name add. So this is a namespace operation, partly, right? We're adding the name add to the current namespace. And here's proof. All right? But look at add's dunder qual name. It also knows about the name add. So I said objects don't know their own names. Well, this seems to contradict what I said earlier. Unless I go change its name. Right? So now this object knows its own name, but it knows it by a different name. So, right? So I would say, yeah, it's still true. Objects don't really know their own names, or may not. It's convenient for a function object to know the name it was created with, because then error messages, for example, look nice. So now if I try to access multiply, what will happen? So I changed the name that the object has as an attribute. I didn't add or delete or modify the current namespace, right? So def add adds a name to the namespace, but add.dunderqual name equals multiply doesn't do anything to my current namespace. I'm changing the namespace of the add object by changing its dunderqual name attribute to be a different string, or refer to a different string. But this name error shouldn't surprise you. Well, no. It's okay if it surprised you, but when you think about it, you're like, oh, right, it couldn't have. There's like if an object, if attribute access, if an object could change the namespace you're running at, well, it would not be good. All sorts of terrible things could happen. All right, that was only half joking. Like actually all sorts of terrible things would happen because people would write code that goes and reaches out to the calling namespace and changes it, and then code would break. But it was a good purpose. Okay, so if I look at add qual name, it's still multiply. Right, and add is still, so what if I look at this one? Yeah, it thinks it's multiply. Right, so now it thinks it's that object, whereas earlier we looked at add and it said it's dundermain.add. Now it says it's dundermain.multiply. How about here? Can I do this? Yeah, you can always do this. If you have a name equal name in Python, the only way it will fail is if the right side isn't a name that's defined yet. Otherwise, it will work. It will do something. It might not do what you want, but it's not going to give you an error. And now multiply has been added to the namespace. Cool. Let's see, let's look at Dunderdict. Why, Dunderdict? Functions have a Dunderdict? Well, they do. And it's empty unless you add something to it. Why? Well, I don't know historically why, but it comes in handy every once in a while. Actually, I do know why. Why it's writable, I guess, is a question. Like there are lots of attributes of function, but why would you be allowed to add to it? Well, it comes in handy occasionally. So function execution defines a new scope. When the function is called, a namespace is created. Parameter names are bound to the function call's arguments. Okay, you notice I'm using arguments and parameters specifically in two different ways. Arguments are what you pass to a function. Parameters are what you define the function with. Okay, and that's if you, I don't mind if you mix them up, but if you use them that way precisely, then you'll be following the Python documentation because they are two very different things. All right, so I'm going to create a namespace and bind some names to it and then throw it away. All right, that's what happened, right? The add function got called, a new namespace created, the A was bound to 2, the B was bound to 3, it was, some bytecode got run to actually do the addition, and then the return returned the 5 to me, and then the namespace got thrown away. Okay? Default arguments. You've seen these before. So when I run this, they are expressions evaluated when the function is defined. So when will the P1 equal print, the print in the signature, get evaluated? And when will the P1 has value P1 get evaluated? And the answer is, when you define the function, that's when the first argument, when the P1 equals happens, right? Can anyone think of a good reason to have a P1 equal print as a default argument? No. Right? And then when we call the function, is it going to print that again? Right. Okay. And its value is none because print returns none. How about this one? What's going to happen here? Well, we know P1 defined is going to print. What about P2 defined? Who thinks they are? Who's confident they know the answer? Just to get a sense of how many. Ah, good. And this is me, right? Like, the reason I do this stuff is because I was, people were asking me questions, and I go, I don't really know how that works, so I go figure it out. And little by little, I was just 2 weeks ago, no, 3 weeks, about a month ago, someone said, well, yeah, we have to remove the compiled bytecode, the .pyc files in the Dunderdict folder, because like if at module execution time, when it's loaded, when it's compiled, it's going to define, like, if we have like if in a module we have some date equals datetime.now, well then when we run it 2 weeks later, it's going to get that out of the PYC file. I'm like, oh yeah, that's right. And like afterwards, I'm like, wait a minute, no, that can't be true. Right, but this stuff is confusing, and I get confused too. So don't feel bad if it's like, well, which way does it work? But it helps to know how it actually does work. So the answer is, we know P1 is going to print. Will P2 print? The answer is no. Right? When we call F1, P1 defined won't print, but the second one will, because it's only when we actually call F1 that the F2 function gets evaluation happens. Okay. And if I call it again, well, P2 got defined again. If you're curious about that, well, let's look at some of the attributes on functions that are there on purpose, not that we added. All right, so F1 is a function. It's a name bound to a function, happened because we did a def in the current namespace. It's got a code object. And that code object has some constants. It's got a none, probably because it was returned. I forgot what it does. Oh yeah, the pass is going to return a none. P2 defined, and then it's got this code object F2. It's got a name for the F2 function as one of its constants, and it's got the string literal that it returns. Oh, it doesn't return none, but F2 does. Okay. I may have misspoke on the none there, because this is F1 code constants we're looking at. So if we look at code constant sub 2, that code object, and we disassemble it. All right, so there's F2, there's F1's code constant sub 2, which is F2. So you can see that the function I didn't ask this question, but I just showed you the answer to the question, which is, when does this code get compiled? And the answer is, when we evaluate. So this code is already compiled before we called it, but it's not evaluated. And the default parameter values don't get done until then, until we call F1. Okay. All right, so F1 is quite simple. It just returns none because it has a pass. Remember, I should put this closer so we can see it. Right? F2 has a pass. So F2, which is F1's code's constants element 2, is very simple. F1 code is a little bit more complicated. And look what it does. It loads the constant, which is that code object, and then it makes a new function object out of it. So it didn't have to compile it, but it did have to create the object with the stack and all that kind of stuff. Or, well, some of it. Store fast, load fast, call function. Okay, we're going to move on. Don't ask me anymore. You've exhausted my knowledge about exactly what's going on with all those opcodes. Okay, function annotations. Well, here's an example of one. And that's where it shows up. It's just a dictionary. And its type is dictionary. Surprise, surprise. These are arbitrary expressions. Sorry, it got a little wide there. Right, so I could do math in there. I can say B99 plus 1, call the length of the string. Like, there's nothing magic about, this is just normal Python. And Python sees the names and the operators and does whatever, and whatever object is returned, or more likely just dereferenced from the name, is what goes into those annotations. Okay, your turn to play a little bit with some functions. Okay, I'm going to go ahead and move us along, even though I expect not even half of you are done this yet, just because I want to cover all of it if I can. And this stuff isn't quite as interesting or hard to figure out as some of the other stuff. This is just showing you how star args and star keyword args work. If you probably already know or figured out from this that basically Star args basically lets you do variable number of arguments, arbitrary number of arguments or keyword arguments, and it will collect them for you. And then you can see the various ways it collects them based on how you pass it. And then we say, okay, what if you create a dictionary and iterate over it? Well, iteration over dictionaries just iterates over the keys. And that we get ready to say, let's pass it a tuple, pass it a dictionary. Okay, it just passes it as a single argument. Whereas if I say star t, it says, please unpack that iterable into multiple arguments, and then it packs them back up into star args. So if you call star d, it's just going to give the first two, the keys, as multiple arguments. This won't work because star star only works on a mapping type, like a dictionary, usually, whereas the star star d does hopefully what you expect, a equal 3, b equal 4. Okay, so following our theme of namespaces and their operations, we've talked about assignment and del and def names. The names in the signature are names that live in a namespace when the function's running. And then we looked at attribute setting and deleting. All right. So a scope, what's a scope? It's a section of Python code where namespaces are directly accessible by using a name. In directly accessible namespaces, use a dot. We've seen that. Namespace search order. Innermost scope contains local names, local to a function. Namespace of enclosing functions, then it searches out. So if you're running a function and you use a name that's not, doesn't exist in that function, otherwise hasn't been assigned in there, then it goes and looks in the enclosing function or class, it just keeps going up. Eventually, it will look in the current module's global names. Well, the current module here, the interactive prompt, is just whatever namespace that is. And then there's an outermost scope, which is built-in names. All namespace changes happen in the local scope. This is tricky, and I'll show you some examples. You should avoid reassigning or rebinding built-in names, but we're going to do that because, hey, it's fun to confuse people. No, hopefully it doesn't confuse people, but we'll learn some interesting stuff about names, maybe. So there's the length function. So if I call def f print line a len, it's going to print line a and same as cell 41. Built-in function len. Oh, not quite, eh? That's because one's the rep, one's the SDR, I think. Is that right? I'm not sure. Let's keep going. I might poke at that later. I did that already. Okay, so now let's do something more interesting. Let's define a len function inside the f function, which doesn't do anything. But when we print len inside that function, we're going to get something different, right? So it's going to show us function f.locals.len. Nice. What if we do this? What's going to print? Line B is going to print first or second, right? First it's going to define the function f, which is going to define the function len. It's going to call the function len, which is going to access that same internal one because namespace is going to look up the name len, find it in the current namespace because it just got added the line before or the block before. And then in line B, it's going to print len. There is a new namespace again. It's going to look up into the enclosing namespace to find its own name, in a sense. And then line C is going to print the same thing. Good. Okay, how about this? What's this going to do? I'll go ahead and define it. So line F will print first. It'll print the internal function. Then line E is going to run and print out the string short, right? Okay, cool. So len, what's len? If I just type len now, what do I get? Yeah, it's going, because it's in this namespace? No, because it's in the built-in namespace, which it looks in after it looks in the current namespace. Right? All right, so here's what you shouldn't do because it confuses readers, at least people like me who know that len's a built-in. So now if I look at len, okay. Now if I define that function and call it, what will I get? It's going to do something. Is it going to give me an error or just not what I expect? Type error being what's not callable? It's going to say len's not callable? What's it going to call? It's going to call 99. 99 doesn't know the name len. I'm picking here, but just again, I'm just forcing you to think about names and objects, right? By the time this happens, it just says the int object is not callable. Yep. So you're right, but the error, the actual error is, well, again, it has to be that by the time that call happens, it's forgotten about the name, it being whatever context that is. Okay, so now if I look at len, still 99. If I del len, is that going to do what we think it's going to do? What do we think it's going to do? Remove it from the namespace. Okay, so now if I look at len, I'm going to get a name error? No, because it goes then and goes and looks in the global namespace. Now what's this going to do? Kind of cool, eh? Right? So del can't operate on the built-ins, so if you do del and len here, it looks in the local namespace and says, sorry, I can't find it. So del is the case where it actually doesn't go look further, which is kind of interesting. Helpful? I doubt it. I don't think that'll ever come in handy for anyone, but it's kind of cool. All right, and len is still there, of course. So print len walk. Print len was this, but it was defined when len was 99. What's it going to do? Is it going to work or fail? It'll work because names aren't looked up ahead of time, right? So that function knows it's supposed to look up the name len, and it does it when it executes. Yep. All right, pass. Pass equal 3. Oh, so len I could assign 99, pass I can't because pass is a keyword, not just a built-in name. And it also is a keyword that gives me the syntax error in this case. Here are the keywords, by the way. And yeah, these are really the only identifiers that don't refer to objects because they're compile time mostly. Anyway, function locals, okay. Value equals module, like it's at the module scope. So let's do, this is going to print module. Actually, yeah, it does, prints module, okay. This one, value, if I look at the current value of value, sorry, that's a bad name after I changed it to be better, and now when I read it out loud, it's a bad name. Value, that name, is the string module. If I call test local, what am I going to see? Right? So it runs, and down there, value got bound to inner, and I print inner. All right, how about test unbound local? What's that going to do? First, I'm going to print the value, so you might think I'd see module, and then change it to inner. Module. And here's the famous unbound local error. Who here has gotten an unbound local error before? Yeah. All right, so local variable value referenced before assignment. Yeah, it didn't change it. Okay, well, let's look at this one and see what's going on here. There's the code arg. There's a whole bunch of stuff in here. There's the arg count. There's the name. There are the names used in the bytecode. Print is the only one. Just let me back up here and remind you what that function looks like. It's just a print value and value equal inner. It's got the number of locals, which is 1. So it already knows that before I run it, it knows that there's one local. And that local is the name value. Okay? So if I look at this, here's the, just to redefine. So if I put value print or print value. So assign the value, like do the name binding, then do the print, or do the print, then the name binding. One works, one doesn't. And it's because they both have inner and none is their constants. I think that's a mistake, sorry. I think even this one might be a mistake. I'm going to delete it so I can remember later when I go check on things. Okay, so if I, oh no, it was a mistake. I remember what it was. Okay. So here's the local version. Oh, I know what happened. Sorry. Didn't survive my last hour editing. So there's the local and there's the unbound local. What's the problem here? So look for the store fast and load fast. At 2 and 6 in the first one, at 2 and 10 in the second one, but they're reversed. So unbound local errors happen because when Python compiles the code, it sees an assignment. It sees an operation that changes the local namespace, and it says that's a local because all namespace changes happen in the local namespace, locally. They don't go out by default, right? And so it marks it in the code as being, oh yeah, that's a local. So then it tries to do in the second one down here, cell 86, it does a load fast of whatever was in that name, bound to that name value, the name was bound to, and then it calls the function to go access it. So this is basically sorry, what is it in Java when you have a variable that's not initialized? This is an uninitialized variable in Python, which you usually can't have, but you can have it here. So that's what's going on. Oh yeah, I was just sorry. I tried this fancy stuff and it works, but then I forgot to show it to you. And it doesn't work anyway because it's too wide, so I don't have to do the old way. So forget all that. So, and then here's the actual, from the fact, the programming fact, why does this fail? That tells you why. You can explore these on your own if you want. What about global? Well, what does global do? Global says this thing that looks like it's local because it has a namespace change, like an assignment, it's not local, it's global. So go out and get it from the global namespace, the module level scope. Okay? So here, I look at the value, it's module, I call test global, and I should get print B module, print C inner, and I look at value, it should be changed from module to inner, and it works, right? And here, if you look at the same thing, you'll see no load fast, it's a load global. So they changed what gets actually done there. Okay, got 2 minutes or so to look at non-local as the exercises. How many are done? Another minute. Okay, we'll move on. Before I do, let me ask a question. When I'm talking, am I going too fast through the material? Raise your hand if it's too fast. Raise your hand if it's too slow. So it's about right. In terms of the time I give you on the exercises, I expect, how many think I know I'm finishing, I'm moving on before most of you get done. How many of you are unhappy because of that? I'm going too fast through the exercises. Too slow? About right, okay. Thanks. Okay, so non-local does what you would think, maybe, is that it says it's not the same as global, go all the way out to the outside, but it just says go, instead it's not this one, but look up until you find one, which might be a global. And you tested this and saw what's going on. Right, so it changed it in there, but didn't go all the way out to the global and got it because it found it here. So it didn't find this one. Oh, okay, so unbound local error, just like a regular assignment, right? Def is a namespace operation. How about this one? Unbound local error. Okay, so again, sort of mirroring what we did with deleting len at the other level. Okay, I'm going to go through this real quick. I think this doesn't, yes, okay, so, okay. I just want to do a quick overview of what are the built-ins, and I'm not going to explain any of this code. But basically, we got 144 built-ins, and 67 of them are exceptions, 77 of them are not, are the rest of them. The exceptions are all of those. And here, if you look at this place, you'll see the hierarchy. Notice that exception is not the top of the base exception is the very top. You should never catch base exception or have a bare except clause in your code. If you really need to, you can do an except space exception. The only time I would recommend that is if you're like at the very top level of some code and you want to catch it, do some logging, and then exit. Otherwise, you should always catch exceptions as precisely as you can, as far down the hierarchy as you can, and over as small a chunk of code as you can, to have your try block. Have your try blocks as short as possible. Let's actually go look at these things. What's left? Well, we got, these are the other ones, most of which you, I'm guessing a third of those will be familiar with to you, right? Bool, none, false. Yeah, so here's, don't use a bare except. Use exception if you have to. And the reason for that is there's no point in catching a system exit or a keyboard interrupt or a generator exit for sure, or anything else. Like, okay. So what's left? Well, there's a bunch of types and built-in functions. And here's what they are. The ones that are types, bool, byte array, bytes, class, method, complex, etc. And then there's these built-in functioner methods. So those are all the names that you see in the, that you can get at with the built-in namespace, except a few others, like IPython stuff, true, false, ellipses. Okay. So more namespace operations. We've covered all of these, plus global and non-local. And when you do an accept exception, well, there's the as name, so that's actually a namespace operation. Adds that name to the namespace, or changes the one that's there. So there is a function called locals. Has a bunch of stuff in it. sorry. All right, so in the REPL, the read eval print loop, locals and globals are the same. So I can do that and then look at the value. I can actually change the value, but you shouldn't do that. And here's an example of why. Sorry. Right? It ain't going to work the way you think sometimes, right? So locals, there's something called fast locals. So I have yet to see a case of globals or locals that I thought I was sort of okay with in terms of actually changing something. Again, in production code where it matters, right? There are cases where you're just hacking around, well, do what you want. But if you're writing code that other people have to read, including yourself after a while, like 6 months later, avoid it. Let's look a bit at the import statement now. Any questions? Okay, import statement. So before we do that, I'm going to create this version of dir that only shows me the new names. All right, so if I do an import CSV, it's a namespace operation. It's not only a namespace operation, but import takes the name CSV, which doesn't exist in the namespace, or might not. It goes and looks for a module with the name quote CSV quote, like it looks for that string. It imports that module or grabs it from the already loaded modules, and then makes a name in the current namespace, CSV, which refers to that module. That's what's going on. Okay, so see if I'm telling the truth. Yes. Right, so now if I access the name CSV, I won't get a name error. I get, oh, it's module whatever from wherever it is. And I can look at its names, or at least its names that don't start with an underscore, because I just want to hide some of that detail for now. And I've got all this stuff. Okay, so I can access an attribute of that module object, and there it is. Yeah. Remember what error this gives us? Attribute error, that's right. I couldn't remember myself. Not a name error, it's an attribute error because modules are just objects in terms of name lookup. This will fail, right? No, it works, okay. Yeah, be careful. Don't go poking around in other people's modules, please. Oh, this is even worse. Look at that. So there's nothing stopping you from doing this, right? Python's, hey, do what you want. So don't do stupid things, right? All right, let's do from CSV import reader as CSV reader. So what that's going to do, from CSV is not going to change the current namespace. Import reader is going to look in that module that it found, its namespace, as CSV reader, that's going to go into the current namespace. So this will only add one name to our current namespace, which is CSV reader. And so there's CSV reader, the new one that got added. And CSV.reader and CSV reader are two names for the same object. All right? Okay. Yeah. Well, who did that? Okay, so let's delete CSV, which is going to remove the name from the namespace, import it as CSV module. So now I've got CSV underscore module as the name in the current namespace. And CSV module reader is CSV reader. Is this going to be true or false? I imported it after I changed it. Is it going to like give me the fresh copy? No, once the module is imported, it just stays there. It's not going to import every time you ask it to. Once it's imported, it just leaves it until, until it exits or cleans up, I guess. So that's going to be true, even though it's now the writer. Okay, so kind of obvious, but maybe not. What is math going to, if I hit enter here, what happens? Name error, name error, name error, name error. You get the idea. There's all these name errors. So why doesn't this give me a name error? Well, it's because of what I said earlier. Python sees the import statement special. It's not just a function, it's a statement, and it treats that identifier as a name that it should find and add to the namespace. So it actually doesn't look this up. It doesn't try to dereference that name by looking in the current namespace, because it's adding it to the current namespace. So it's sort of like the equal. Right? So that works. I can get rid of it, okay. If you need to import something that you don't know the name ahead of time, you can use the import lib module. So this will import the math module, right? Okay, so if the math module is imported, can I do this? No, because import lib import module is just the function. It's not smart. It doesn't know how to change the current namespace. Again, because if you just called some arbitrary function and it could change the calling namespace, that would be awkward. That would be lots of problems could come from that. So if I try math.py, I get nothing. But you notice that what it returned was a module object up there, right? So if you want to use the import lib module and you want to add the name to the namespace, you've got to do it yourself. And here's the way to do it, right? So now I've added the module to my namespace. So is math.py going to work? No, because I've added math_module as the name. All right, so math module py works. Okay, just names. It's all about names. Okay, suppose I do module name equal math. Well, now I'm just having fun with you. So is this going to work? Why is it not going to work? Because it's going to look for a module called module_name, not what that dereferences to. Because it doesn't dereference, because it's an import statement. So it's a weird name. It's a name that it doesn't actually look up. Okay, so that's going to say, I can't find that module. But will this work? Invalid syntax. You can only give a name with the import statement, okay? And again, I think this was mostly obvious to most of you, but now it's really obvious. All right, so here's the right way, import math. And how are we doing? We got, I don't see people waving their hands. It's like 9 minutes to 3. You're going to wave your hands when it's getting close to, what's that? 5 minutes, okay. I'm trying to decide whether to cover this or not. I'll cover this on I'll do this in part of the next section. Or maybe not part of the next section. So these exercises you were going to have, but I'm going to stop you from doing them. No, I'm not. I'm going to do them for you. So import lib. There is a reload function in the import lib module that will reload a module if you need it. The only time you need it really is if you're doing development or something. Again, very rare that you would want to do, unless you're doing some really crazy stuff, that you'd want to do it in production code, for example. Okay, so will this work? And if not, why? Right, so Python's going to look at this name, finds it, because it was imported, look at that attribute name, find it. It's going to look at this name and say, I can't find that name in the current namespace, and it's not in the built-ins. Thank you. I'm thinking, why did that work? Right? Reload. Reload argument must be a module. Okay, so now if I import CSV and then reload, I passed it a string. I didn't pass it a module, right? So the right way to do it is just do a reload and pass it an object, which is the module itself. Okay, so this one I'm not going to start because it's complicated, so we'll break early, 7 minutes to. So then 20 minutes is the break, I believe. So if you could come back by 3:10, 3:13. So while we're waiting another minute for others to come back, I'd like to encourage you before you leave or after you leave or sometime, do the survey. It's really helpful. I used to run the tutorials here at the conference, and it's really helpful to have that kind of feedback from you in terms of what's working, what's not working, etc. Happy to get feedback. Like the reason, every time I give a tutorial like this, I learn something from the audience. At least, and usually it's like 10 or 15 things. And then I fold it back in. So the reason this is as good as it is, I'm not saying it's great, but it would not be as good as it is, except that people who before you gave feedback did that. So please pay that forward and give me feedback and say this would be clear, or this was unclear, use that instead, whatever, okay? Okay, welcome back. I think there's a couple people missing, but they'll trickle in. So, any questions before we get going for the second half? Things you were thinking of during the break, chatting with people about? Okay. Let's look at augmented assignment statements. So if I bind two names to the same object with that first statement, and then check if they're the same, of course they are. If, on the other hand, so then I change string 2. Again, am I changing string 2? Well, yeah. String 2 is a name that's bound to an object. I'm changing it by binding it to a different object. I'm not changing the string ABC into ABCD. Strings are immutable in Python, like numbers are, so you can't actually change the object itself, as opposed to many objects in Python that are mutable, like dictionaries and lists, et cetera, where you can ask the object, change yourself, add this new element to the list, for example. So if I run this line, I'm going to get string 1 is string 2 is going to be false, right? Because it actually did change one of them, right? And you can see that string 2, well, see, there I go, say it again, it changed one of them. It did, in terms of, at the variable abstraction, level of abstraction, yeah, it changed one of them. The names which were bound to the same object are now bound to two different objects, one of which is different than the first one, because the plus basically took the two strings and created a new string, and that's what string 2 was bound to. If I do it with a list, right, and here, will I get true or false that list 1 is list 2? Right? Because again, list 2 plus D is saying take what list 2, that list, and concatenate it with this other list with a single character D, and create a new list, and then rebind list 2 to be that new list. Okay? Let's use the augmented assignment statement instead. So we do a string, and we get the same as we did before. We do it with list, and we get different behavior. Okay? So what's going on here? Well, list plus equal and string plus equal mean different things, and here's why. So plus equal is not just syntactic sugar for equal and then plus. Right, so let's look exactly what's going on here. So we're going to look at some code, again, some bytecode. Notice line number 4, binary add at the top, in place add at the bottom. Right, so plus equal is a different bytecode operation. It's an in place add. And in place add means different things to different objects. In fact, that the documentation clearly states that, which I'll show you in a moment. So let's just play around with that a little bit. Here's list 2. If I call list2.iadd d, which is the same thing, that it accomplishes the same thing, right? So it's sort of like I showed you before. It doesn't use the same bytecodes, but it gets to the same effect, has the same effect. Then I get not only does the list change, but I get back. So iadd returns the changed. So it tries to change the object and it returns the changed object. So if iadd changes the object in place and returns the changed object, what is string 2's dunder iadd going to do? Oh, good. Because I couldn't think of anything it could do that would follow the rules, right? It's supposed to change the object in place. Well, you can't change strings in place because they're immutable. So if strings dunder iadd doesn't exist, then how come it works? Well, it's because if a specific method is not defined, the augmented assignment falls back to the normal code. Okay? So basically, when you do a plus equal, what was it called again? In-place add bytecode is what it gets compiled to. The in-place add bytecode goes and looks for a dunder iadd method, or at least that feature, in the object. I'm saying it that way because, again, I'm flipping between the different levels of abstraction. In the C code, does it actually go look for a method on the object? Well, it's going to look for what implements that. And if it doesn't, then it falls back and turns it into the other. Okay, and you can see, well, okay. So here's something kind of unusual. Let's try this. If we have a tuple, and we do an iadd1, what's tuple iadd going to give us? Any idea? Why would it give us an error? It will give us an error. Why? That's right. They're immutable, so I should get an attribute error. All right? So if I do this, right? So here I got the error because it tried to look it up and couldn't find it. Here I got the error because it tried to run the in-place add and got to the point where it couldn't do item assignment. I can do this though, can't I? Yeah, of course I can just add things together. Oh, no I can't because I tried to assign it, right? So on this part I can do, but I can't do the left side, the tuple one, and then the assignment. Right, and you can see that it didn't change. Phew. However, what if I do this? Let's make a tuple which contains a single element, which is a list, and let me do a plus equal of the 0th element, which is the list 12, 13, asking it to modify itself to be the list 12, 13, 14. Oh, no, okay, good. So it also fails. But check this out. It changed it. Right, so this is one of the warts. If you go, there are lists of Python warts, they're usually called. There are 5 or 10 things where, these little edge cases where Python doesn't do what it really should do. But competing with that are Python should be fast, Python should be easy to maintain, Python, all these other things, right? And so when those are in tension, at some points people say, well, yeah, okay, so you got an error. It did a side effect, which in a sense, in some pure notion doesn't make sense to do, but to fix it, we'd have to slow down Python so much that, well, that's, we're not going to do that. And that's not quoting any core developers, by the way. That's just my intuition in terms of why that's the case. But if you actually want to see what's going on here, I'm going to go through this fairly quickly. So I think only, I just don't know this is kind of interesting, kind of not. So I'm going to fly through it, and most of you won't get it, and because I want you to get the stuff that's coming after this. It's more important. But basically, if you sort of do this one step at a time, and basically, don't worry if you're not following along. You can look at it later, and you may or may not find it helpful, right? So it does the first step, and then it does the second step, and that's where it does the fail, right? So basically, if you turn that into what's actually happening, and you can look at the code here and see what's going on, and there's an explanation in the FAQ that says, here's why this does what it does. Okay. Function arguments are passed by name binding. Anyone ever asked you the question, is Python passed by, I've already forgotten, call by reference or call by variable? Call by reference or call by name, thank you. Call by reference or call by name. And the answer is, well, it's name binding is the way I would describe it. So the local name is dereferenced, and the reference to it is passed in, and the name in the function is bound to that same object, right? So here, let's just see how this works. Define a function. So if I call function 1, can function 1 change string 2? Good answer, which means I'm not asking the right question. Can it change the string that was passed in? Can it change red to something else? And the answer is no. So it does that rebinding, right? So red was passed in. String 2 at point B is red and blue. It's red-blue, but when I get back to the outer scope, it's unchanged, right? And you can tell, like if you actually change this to, instead, like the plus blue here and the red, like here, instead of passing in a reference, which was the reference or the name string 1 right here, I just pass in red directly. And instead of the plus equal, I'm passing an equal, because that's what this falls back on with the, because the Dunderdict operator isn't there. Then you can see that, of course, it can't change that. Of course, you're going to get red back. And of course, red is red. Good. Phew. So if we try this list, however, like if you look at this code right here, uses plus equal. This code uses plus equal. Right? So while it kind of seems funny that one can change it and the other can't, it totally makes sense if you know that the object is being passed in, a reference to it. The name is bound to that object. If you ask the object to change itself with plus equal, well, in strings case, it falls back and does a name reassignment, a name rebinding. In lists case, Dunderdict is implemented because it can change itself, and so it does. Okay, so if you're wondering how it works, it depends on as long as you think about the names, the parameter names being bound to the arguments, and then think about the operations and what they can and can't do to the object, then you shouldn't get confused. Or you're less likely to get confused. You probably still will, just like me. Okay, any questions? Classes, let's look at the class statement. Class statement starts a block of code, blah, blah, blah. Yeah, so just like function, classes take that name and they add it to the current namespace with an object that gets created from Python compiling all that. And the object itself has a reference to the name because it's nice when you get errors. It's nice for an object to know, a class to know about its own name, just like it's good to have a function know its own name. All right, so we'll execute that. Now let's look at the class. All right. So it's called Dunder main number. It has a name. It has a class. What's number's class? Do you remember? Close. Remember, there was type in between. Classes are of class type. Because the class is a type. Types are of type. It's got the version that we defined up there. You create an instance of a class by calling it, right? That's the way you instantiate it. So there we go. So what happened there when I called it that way is that the Dunderdict was passed an object. So Dunderdict is not a constructor in the C++ sense. It doesn't create the object. The object gets created first by Python using the Dunderdo method, which is rarely overridden. I think I did it once in 15 years or 12 years or whatever. So it's created for you, and then it's passed to Dunderdict. Dunderdict initializes the object. So subtle difference there to keep track of. So I've got this. So now if I look at numbers.add, function main number add. Okay. What if I look at the instance n1, look at its add attribute? So function main number dot add, bound method number dot add of, and then this number object. Well, this number object is the one that n1 refers to. So when you look up a method on an instance, it goes and finds the function that's defined in the class, which we call a method, and returns a bound method object. So there's some magic going on in between there. And then I can call it like this, of course. Woo! 1 plus 2 is 3. So the type function, the class statement, is just a way to call a function, take the result, put it into a namespace. Great talk. I encourage you to go watch it. It's a little bit dated, but I don't think it's dated, meaning I can't remember last time I watched it, but I don't think it's out of date. So the default callable that gets used is the type callable, right? So type we've used a lot in here. We pass it an object that tells us what the type is. Well, if you pass type 3 arguments, it goes and constructs a new type. It creates a new class object for you. So let's do that. Let's define a new init, no dunder, and define an add. So these are functions that I'm adding to the global, the module level, the read eval print loop namespace. So now I'm going to call the type function, passing it the name of the class, its superclass or superclasses that it inherits from, in this case none, so it's an empty tuple, so it's going to just inherit from object by default in Python 3. And then I pass it an attribute, a dictionary of the attributes. So I want version to be 2.0, and I want Dunderdict to be that function object, and I want add to be that function object, right? And it works. Type of N2, N2's class, N2's Dunderdict, N2 amounts, N2 add. So it all works. So that's the way you create a class without using a class statement. Right? And you notice number appears twice. Right? So when you do it manually, class statement does that for you. It creates it in the namespace and it tells the class about the name. Well, here we have to tell the class about its name manually. And you see that with named tuple, collections.named tuple or named tuple, same thing there. That's why you have to pass the name twice, or type the name twice. All right, let's look in some of the internal structure here. So here's my class again. I added a print. There's number, version. So numbers dunder init is going to be a function object, right? Yep, function. Numbers add is also going to be a function. If we look at the attributes of number, the class, we get a bunch of stuff. Dir. When you call dir on an, we've used dir with no arguments and it shows the names in the current namespace. When you call dir on a function, sorry, on a, yes, on an object, thank you. I forgot to, actually, I was going to put this in. Oops. If called without an argument, blah, blah, blah. If object supplies a method. If the object supplies a method named dir, it will be used otherwise. Otherwise, it returns its attributes and recursively the attributes of its bases. Right? So it's not just the attributes of the object. It's the basically it's the attributes that you can get to from it. So that's what dir does. There's all these attributes, one of which is the add. Yeah, they're all the Dunderdict and the add, and then a bunch of others that we didn't define that it's inheriting from some other places. Okay. Well, no, not quite. Everything isn't being inherited. The Dunderdict isn't. I think that's actually on the class. Sort of. I'm not sure if it's actually. I suspect it's not limited to the class. I suspect that's the one that does the inheritance. But let's just look at the public methods here. So if we look at the public, the not the dunder ones, we get add there. Okay. So N2 has an amount. Yeah. It's all making sense. Looking for any nods, heads that are shaking. No, I'm confused. Okay. There's the bound method. There's the bound method, right? So n number.add is a function. n2.add is a bound method. If we look at the public or the not dunder attributes, we have add and amount. So add is the method it gets from the class. Amount is the attribute that gets created in the Dunderdict initializing method. Okay, what's the difference between these two? Well, just the amount. Not surprising. And here you can see the dictionary with the amount. Number, the class, has its own dict, and it's this mapping proxy, which has all sorts of interesting stuff. If we look at its dicts add, oh, there's the function again. So that's the other place we can get it, number.add or number.dunderdict add. And in fact, they are the same. So those are two names. Two names, and not quite. This is an entry in a dictionary, and it is a reference to the same object that number.add name is. Okay, so anyway, we got this bound method, we call 3. It works. So here's what we defined earlier as add, and there's the function. So what will this do? If I call class name dot add and pass it the number 2. What kind of error will it give, do you think? How's it going to fail? How is this function going to fail when we pass it the number 2? Wrong number of arguments, yeah. Right? So we try that and it says, sorry, you need 2 arguments, not 1. Can I do this? Right number of arguments. Sorry, someone said wrong type. I'm going to object to that statement. I don't care what the type is. We like duck typing in Python. Duck typing meaning, does it have what you need to make the code work? Well, what's add going to do? It's going to try to access the amount attribute of this first argument. And int, I don't think the integer object representing 2 has an amount attribute. If it did, this code would not fail. It might do the wrong thing, but it wouldn't fail. So the way this is going to fail, it's going to not find the amount. There you go. Int object has no attribute amount, right? So whoever I was correcting when they said type, no, you're right, it's the wrong type. But again, think broadly. It doesn't have to be the right type as much as have the right attributes, the right behavior. Okay, so will this work? Yeah, because it matches the function signature and the code. It's going to run, it's going to find the amount, it's going to do the right thing. Okay. Of course, this is the right way to call it. Okay, well, let's, there's what we had defined earlier. And you can see it shows us a few things about what it does. It gives you the docstring, etc. Okay, let's monkey patch. So I was trying to figure out if I was using the name monkey patch correctly in here, and I think I am, but if I'm wrong, I'd like you to tell me. Like, I know it's used specifically talking about testing, and I went and looked it up and thought, yeah, I think this is actually the correct usage, but I'd be happy to be corrected. So anyway, I'm going to monkey patch. Let's create a new function in the current namespace, and let's just have Dunderdict point to that function in that function object instead of the original init. So now numbers Dunderdict shows us this function. We can see that it knows it's called set double amount, so that gives us a clue it's the right one. We can look at its help, and we get interesting. So slightly different because it has an, oh no, I guess it is the same because initial amount we use the same arguments. All right, so let's create number 4, and I'm thinking it will be 4 because it's going to take the 2 and double it before it assigns num amount. Phew, good. All right, and of course it's got an add method, and I can add 5 to 4 and I get 9. I can look at its init method, and it gets the bound method. Let's do a multiply by now. Thank you. There we go. Yeah. So are these at the same address? No, they're different. So when it returns that method, it binds it to the object, and so you get a different, they're actually 2 different objects. Okay, so let's define multiply 2. Hmm?
It's showing that M2's init method also got changed because we're referencing the same parent class.
Mm-hmm. Yep, good point, right? So when I changed numbers.init up here, you can see numbers.init is now the set double. Well, here, when we do N2, which was created before we monkey patched, we can see that it's the same object, right? So it's when you access the attribute Dunderdict, when you access the attribute of an instance and it can't find it in the Dunderdict of the instance, it goes looking in the class. And if that class has changed in between, well, it does it right then. So that class number has set double amount as its Dunderdict when we evaluate this, so we get back a different bound object, a bound method. Okay, so let's define the multiply by. And now for this next section, don't volunteer comments. You almost always appreciate them, but at this point, it'll be more instructive, I think, for some people. So we define the multiply by, great. So I'm going to add mul to the N4 instance. N4 mul equals multiply by. So this instance has a multiply by. And if I call n4.mul, don't answer this question, what will it do? Just think about the answer to yourself. What's it going to do? Missing required positional argument. Okay? So again, some of you are nodding like, oh yeah, I see what you did, but let's let everyone else just stay frustrated a little bit, because it's at that point of frustration where it makes you think a little bit harder and maybe get it before I show you. Maybe not, that's fine too, I'll show you. Right, so I can't call it that way, wrong number, oh right, so I need to give it 2 arguments. Okay, well I give it 2 arguments. Oh. Okay, well let's see if we can figure out what I did wrong intentionally. Well, if we look at n4 mul, it says function main multiply. Let's look at this. If we do n10 equals number 5, and now if we look at n10 mul, what do you think we'll get? Don't answer. So who knows what's going on? Okay, so the problem is, well, let's just keep going. Trust my preparation here. Let's look at what's on N10. Add an amount. And there's the amount in the dict, as we expect, and the add comes from the parent class. If we look at the number class, oh, well, there's our first clue, I think. And there's our second clue. So where does N10 get its amount? From its Dunderdict. Where does N10.4 get its dot amount attribute? From the Dunderdict. But the add on N10 is coming from the number. The add on N4 is coming from, now why aren't I showing this? I should have a Dunderdict in here, shouldn't I? Right here, I think I forgot a line when I changed this a little bit. Should have a N4 dot. Right, there it is. Almost missed the best part of my punchline. Right, so I monkey patched in the wrong place. So when it looks up mul on N4, it gets back the function that I hung off of N4. So the right place to monkey patch is here, right? If you're going to monkey patch a method, you put it on the class, and when you access the attribute, let me back up and say that slightly differently. If you want to monkey patch the method, which is only callable on instances, you change the attribute of the class, giving it a new function, which becomes a method when you access it on an instance. All right? So we'll monkey patch in the correct place. And now bound method. That works. So this should work too, right? What's going on? It's still broken. They have the same public, like the dir, you do dir on either of them, and you get the add amount and the mole. N10's dict. Aha. So I didn't get rid of this one, right? So first time I monkey patched the Dunderdict in number, and everything works down here in the instances. Second time I monkey patched the wrong place, and suddenly this one that had no attribute started working because it found it in the right place. But this one, I never removed it. So now for num n4, when I say give me mul, it says, oh, I found it in my Dunderdict. Here you go, it's a function. If I can get rid of it, and you can see the difference between them, right? One's a method, bound method, the other's a main. So if I get rid of the Dunderdict, what's going on here? Hello? Sorry, I'm having doesn't seem to be happy. I'll just wait for at least half as many seconds as it will take me to restart it. And I ran it twice. Okay, so now if I look at N4 Dunderdict, okay, good. Now, they are both bound methods. Good. 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 Everything works. Huh, we're happy. Okay? So again, intentional errors to make you think about how are these things working. Hopefully drives home the point and helps you remember it. Bound methods. So here's N4. I can take N4's add and bind a name to it. And then it's kind of handy function. Add 4 to 6, and you get 10. Or here's we'll take that. Here I'm using the class I created, the instance N4 I created in the class number. Here I'm just using the built-in int, and I look at its dundermul and I call it double. And I can use that name. It's callable, and it works for doubling numbers. Okay, so that's a trick you'll occasionally see. Instead of writing code, just use existing functionality. Okay, let's look a little bit more at these instances and see what's going on. So there's number, there's N4, number add, and N4 add. So what's N4's got add amount and mul. It's got a whole bunch of other stuff, of course. If I do a real dir instead of this fake one I've been running, which hides all the dunders. And N4 add has just that. Well, let's look at the actual difference between them. So if you look at the number add function and the N4 add bound method, they have all the same attributes, except the instance has a dunder func and a dunder self. Okay, well, what's the dunder self? Anybody good with numbers? Remember that number from earlier? Same number, right? So sorry, I looked in the wrong place. There it is. This is the one to look at. Line 97. N4 is right there. And there, just to remind myself later to do it slightly differently. And you can see that N4, the instance, has a bound method, which has a dunder self, and it is a reference to the same object that N4 is a reference to. Okay? And the reason it has to remember it that way is because the bound method stands alone. You can give it to someone else, say, hey, here's a function, and it's actually a bound method. So it doesn't have the context to go find the, once you do n4.add, the n4 is gone in terms of expression evaluation. How about the func? Let's look at the n4 add func, and it is the same as the number add. So n4 add, the bound method's dunder func is a reference to numbers add function, right? And you can see that they all share the same function, right? So if you look at all the bound methods, you have two objects, you access their method, you get bound method objects, you look at those two bound method objects, they refer to the same function in the class, of which they are instances, and that code object is the same. Of course, they all share it. There's no point in passing around extra copies of the same thing. But of course, the bound methods are different because they have to be different because they have references to different selves. Okay? So I can do this, and roughly what Python is doing is this. All right? So when you say n4.add5, well, the n4.add itself, like the n4 goes away and we have this bound method, it looks at its dunder func, and passes the instance, and it passes whatever we call to it with the 5. Okay? Kind of make sense? Maybe not caught it all, but you're thinking, oh, this is how Python is implemented. It's really simple stuff, really. It's implemented in a fairly straightforward manner. Simple. Let me back up. Once you get it, you're like, oh, okay, yeah. It's not like there's this crazy complicated algorithms behind the scenes. It's just, well, no, when you go access it, you get a different method. It saves those references in there. So again, the point of this is not because you need to go poking around. It's just to think about how it's implemented. Understanding that lower level, you'll be able to function more efficiently and more productively at the higher level, hopefully. Take a few minutes and do a few exercises with bound methods. So the question mark syntax only works in IPython Notebook. If you want to do that in the interactive prompt, you'd type help, open paren, and pass it the object, and it'll give you that help. It's just a nice feature that IPython adds. How many are done? Okay. Sounds like looks like most people are done. So all I'm doing here is just an example of you can do is to see if an element is in a list. In. You can use the in operator to see if an element is in a list. Or you can call dunder contains directly, which is what in will call if it exists. And then you just take that method that's already bound because we pass it, so we're taking this method off of this list, and it will return a bound method. Bound method you can call directly, right? So is keyword. Now, without having to write some function, we now have what looks like a function, and bound method is callable. Just tells if something is a keyword or not, right? So some of these things are just tricks to get you thinking about other ways of solving problems in Python that are more Pythonic, that beginners don't always think of, especially coming from other languages. Metaclasses. Who's scared of metaclasses? Who used to be scared of metaclasses? Like guys like, oh, metaclasses, that's, I don't know what that is. I'm still scared of them, but I think it's now I'm scared of them because I know they're hard to get right, as opposed to I couldn't write one. Like, I could now write one if I have to. I haven't, except ones like this. I've helped someone who was writing one and thought, oh, I wouldn't have done it well. It was, like, use them if you have to, but try not to use them because they're really powerful. There's a project right now that we're working on that we might use them for, mostly for documentation, just to say, okay, in this class hierarchy, what's the best way to figure out what it's like so we can document it and maybe even traverse it? And the answer is, well, if you make a metaclass at the top level that records that data, you just instantiate all the classes as part of load, and then you instrument it and store it somewhere in some easy to read format. There are lots of good use cases for metaclasses. How many here have used metaclasses? I expect most of you should raise your hands. There are all sorts of libraries that use metaclasses and you don't know it. Not all of them. There's lots of good libraries that don't. I wonder what the number is. I wonder if you actually went and looked, I suspect it'd be more like 50% of you probably have used them without knowing it, instead of the 20% that are aware of it. Okay, so a metaclass is just a way to customize the creation of classes, right? So by default, classes are constructed using type. We saw that, right? We did it ourselves. Well, I did it for you. If you pass the metaclass keyword argument, or you inherit from an existing class that included that argument, then instead of type being called, metaclass, whatever your metaclass argument is, in that, right? It's in the keyword argument in the class definition. So it's not a usual keyword argument where you're actually calling a function, but it instead is used, it's sort of reuses the syntax of keyword arguments. Okay, so usually when you want to create a metaclass, use subclass type, because type is a callable, but it's also a class, and you can subclass it. And then you either override prepare, dunder new, or dunder init. But we can just use a function like we did before, right? So treat it like a function. So there's the old example from earlier. And here's a very simple function that is a callable that has the same arguments that type has. And it's going to print the arguments and then call type with the same arguments. And whatever type returns, it's going to return. So it's basically, I'm just saying, okay, usually the class statement, Python collects it up, sends it off to the type function, or the type callable. Instead, I'm going to say, sure, collect all that up, give it to the metaclass, and then I'm just going to send it to the type function. So it's going to create the right type. All I'm doing is adding a print before it does it. All right, let's see if that, so let's try that out. All right, there. You're all experts in metaclasses now. All right, so it shows me, it did that print here before it actually called type to do the real work, and it printed out the arguments it got. So this function I created gets exactly the same argument. Again, that should look very familiar because it's the same ones we passed off to type when we manually created the number class. Okay? Sorry, I had a thought and I can't remember what it was. It'll come back hopefully if it was useful. So then when we instantiate that class, nothing happens. The meta class was already called. So it's when the class object got created. Okay, let's call the underscore dump method on N1. Doesn't exist. You know, I wish all my classes had an underscore dump. Well, here's how you would do it. So I'm adding these 3 lines to what I had before, right? So it still looks like the signature of type, name, basis, dict. I still call type, but before I call type, I update the dictionary that was passed in, right? And this is one of those, usually I recommend not naming local names that override built-in types. Well, this one, if you look at all the documentation, it uses dict here, so I sort of hemmed and hawed and decided to go ahead and follow that convention, right? So I'm going to basically add a new function right here, which looks like a method because it has self, and is going to be a method because it's going to be defined on the class, not on the instance. And then I add that key value pair to the dictionary of attribute of the pieces, the parts of the body of the class. Okay, let's see if it works. I think I've talked about it enough. So now I do that. And this, of course, works. Look at that. It works. Oh, and now I remember what I was going to show you that I forgot to do. Just to say it one other way. Right, so this is implied, is another way to think about this. When you create a class in Python, metaclass equals type, well, you can add that and it won't change at all what happens, because it's exactly that is what happens. Python collects all this stuff, passes it off to type. If you say metaclass equals type, it does the same thing, okay? Okay. So my purpose here was to make you less afraid, to make you less afraid of metaclasses. It's not going to teach you how to write interesting metaclasses or correct metaclasses. To do it right, to do it really well is hard. But do this exercise, and I think it'll reinforce a different way how they actually work. Okay. So remember, this value, and I think I made myself a note to make that clearer in the future. Whatever this function or callable returns is what the class object is. Let me rephrase that. In Python, class, blah, body, creates a class object, binds a name in the current namespace to that object. If you add a metaclass, or one of your parent classes already has a metaclass, then whatever that metaclass returns is what the name in the local namespace is bound to. So whatever object the metaclass returns is what gets bound in the local namespace. So here, this is a function that looks a lot like a metaclass, because it's just like type, it has those 3 arguments, but it returns that object, right? So if I do that, so the class object that gets, what happens is Python takes that class definition, takes the name weird class, it takes the base classes or superclasses, which is an empty tuple, and it takes the list of attributes, which is empty, and passes that off to return spam, and whatever return spam returns is what's bound in the local namespace to the name weird class. Right? That's all there is to metaclasses. It's just code that says, whatever you were going to send to type, give it to me instead, and I'll do whatever I want. Okay? And usually the way you do that is either by calling type, or more likely subclassing, changing dunder init, dunder new, and dunder prepare, like I said earlier. Right? So by now, hopefully it's not a surprise that weird class is just the word spam. Right? And it's of type string. It's not a class object at all. It's just as though I did this, right? So return spam returns that string, and it's just like I did that. That's exactly what the metaclass did. Well, actually, that's actually not true. What it really did is if I passed it, I should make this more clear. It's like I passed it weird class, and I passed it an empty tuple. And then weird class is just that string. Okay? Yes?
Would this be a way using metaclass to, for example, have a metaclass of singleton, which takes a thing, calls type, and then returns that object instead of leaving the class itself?
So the question is, could you use a metaclass to return a singleton where when you instantiate the class, all the instances are the same object? Yes, by overriding dunder new, I think you could do that. However, if you want singletons, there's lots of other ways to do it and it's a fascinating discussion if you go online and look at like Alex Martelli's Borg pattern and others that talk about what do you really want. When you say I want a singleton, usually you want certain behavior, and there are other ways to get the same behavior that might be a lot simpler. That's I'm not an expert on that, but that's sort of from what I've read, and I've wondered the same thing or similar things, and that's what I can tell you in terms of leads to go follow. Okay? Anybody afraid of decorators? No one's afraid of decorators? I can skip this section. Anybody was afraid of decorators? Okay, well then we'll go through it anyway. Decorators are similar to metaclasses. They sound really crazy, and partly they sound really crazy because they do these hard things. Decorators, sort of the base case is even a little bit harder. Well, it doesn't matter. The point is, decorators are the same as a metaclass in that in a class statement, you can sort of get in the way of what happens to that class as part of construction. You can change how Python constructs the class by inserting your own things. Decorator, similar. Decorator is just a way to take a function and give it to a different function and change it and get back our changed function. Now functions, it's kind of interesting to think about if you have some existing code that you want to augment or reuse, but you want to change parts of where it runs. There's only a few ways you can do that, right? So, like I've got code and you can't touch it. I won't let you change it, or you don't want to change it because you want me to keep maintaining my code. How can you leverage my code and change it? Well, one way is callbacks, right? So for example, sort takes a key argument, right? So in the sort function, there's a whole bunch of stuff having to do with sorting, and then there's a little piece there that says, okay, now go get the element that I want to compare to figure out which is smaller. And then it does a whole bunch of other work. Well, you can pass sort a key function that says, well, when you're about to grab A and B, instead, grab A and B and pass them off to my function, whatever it gives you back, compare those, right? And sort has a CMP, I think it's called, argument as well, right? So that's a callback, and that's a way that you can change existing behavior and make it more general. Another way is you can have a class hierarchy, right? In a class hierarchy, you could have a superclass that always has 3 methods, A, B, and C, and then a subclass, you could override B, which is right in the middle. And that's sort of like a callback, but it's a different way of structuring it. A decorator is another way to do it, right? You can take an existing function and then modify that function to do something slightly different. With a decorator, unless you're doing weird stuff like hacking AST, the abstract syntax tree of the compiled function, the only thing you can change is what goes into the function and what comes out of the function. Right? So if you have a function that exists and you want to change the behavior, you can change the arguments that get passed in, you can change the return value that comes back out, but the middle of the function you can't change. So it's one of the ways to leverage existing code. And usually it's used when you have lots of functions, you want to change them all in a way that has nothing to do with what the function really does. Like you want to add some tracing, for example, which is the example I'm going to here. Okay, let's start with simple function. Not very exciting. How about this? So when I was trying to figure out, okay, how do decorators really work? And I'm like, okay, a function that returns a function. My brain hurt for a little bit. Like it wasn't, some things I'm really good at, some things like this, I was like, thinking about that meta level was hard for me. So I was struggling to think of this. Anyone want to admit that they kind of look at that and say, well, a function returns a function? Okay. And it depends on what language you've been working in a lot of times. Like if you've been working at languages that the only way to write a function is you write the code, and here's a function that returns a function, then it's a lot harder. And for me, Python was the first language I worked in. I did some Lisp, but not enough to really get Lisp to get to doing that. So it took me a while to start to think that way. So anyway, this function returns a function, right? So when this is called, not when it's defined, but when it's called, this gets run, and then that gets added to the namespace of the local namespace of createAdder, the enclosing function, and then that object, that function object, gets returned from the createAdder function. And notice that second, so this is a function, the function that gets returned takes one argument, and it calls add with 2 arguments, and one of those 2 arguments wasn't passed to this function, it was passed to the createAdder function, right? So this is a closure. Let's use it and see what's going on here. Add 2 to, I love this name because it sounds so bad until you use it, which is the best kind of function name. It should look good when you use it, not when you write it, right? Add 2 to 3, 5, yep. May not be a good name for other reasons, but I like that part about it. So how does this work, by the way, in case you're curious? Well, add to 2 that came back, the add to 2 object that createAdder returned to us, it's got a Dunder code, and it's got some free vars in it, and it's got a closure, and it's got cell contents in one of those things, and the first was 2. Yeah.
What is the type of that?
Of which?
If you just add 2 without any parameters attached to it, what does it give you?
Oh, two. function, but it's got this stuff. Okay, so here's a function that accepts an argument. All right, so this is a function that takes an argument and calls a function that it got from outside in the scope. Here we're going to take a function, write a function that takes a function as an argument, returns a new function. All right? And of course, what does this function add? Oh, nothing. It's just going to return the function which does the same thing, except an extra layer of wraps it, I guess. But if we add some print statements to it, right? So just adding, the only thing between 9 and 10, or what's going to be 10, cell 10, is I added the prints and the documents and stuff like that, documentation. Okay, so now it's going to print before and after when I move the result. I saved the result so I could get the print in there before it returned it. All right, so now, let's try this. Traced add is a trace function. It's going to take the add function and return a new function that does some stuff before and after, and then calls add and gives me back whatever add returns, but prints it first. There we go. I could actually take add and rebind the name to whatever trace function came back, and then add itself would be a new version of add that had the tracing built into it. Well, not built into it, but wrapped in this new object that calls it add inside. Or I could use decorator syntax to do the same thing. Right? So at trace function says whatever comes after it, Python, when you're all done creating that function object, and before you bind it, before you bind the name add to it that you got from that object or got from parsing that, what becomes the object, instead take that object, pass it off to this function, trace function, and whatever you get back from that function, bind that object to the name, bind the name add to that object in the current namespace. So that's all there is to a decorator. It's a function that returns a function, or that's what it should do, typically, and you put it in front with the @ sign. Okay? Now you're all experts in decorators. How they work, right? Like that's all. So if you were scared of them before, now you should be less scared. Just like, oh, that's all there is to it. Now doing them right, well, we'll go a little bit further here and see what else there is to do. What time do we end? By the way, I've forgotten. 4:40. Thank you. Okay, so there's the trace function add 2, 3. See, it worked. Now a couple things to make this slightly better. You notice that add's qual name is kind of ugly, and its documentation is kind of misleading. It's called the new function. I want to be able to trace anything, not just add. So if I trace multiply, it's going to say, well, it's the new function. If you add wraps to it from functools, it basically cleans all those links up. So now we look at the add function. It's function add. So it's better, but its qual name is add. And it's got the documentation is correct. All right, so you notice that this, oops, where'd it go? You notice this is just, I'm referencing a function. I didn't pass any arguments to the decorator. If I want to pass arguments to the decorator, all I need to do, where'd it go? Where'd it go? Right there. So Python sees the trace function and evaluates it as an expression. It's a name, it resolves it to the object. If it's more than just a name, you could, for example, make it a function call, and it would resolve that by calling the function and using the object the function returns. So that's the way you add parameters to a decorator, is like this, right? So all I've done here is I took the original trace function, which was over here, and I moved it to the right. I put another function around it, another block around it, and then inside, I added a little bit of stuff that references what the new outer function was passed. okay? And all I'm going to do is, if it's uppercase, I'm going to make the returned result uppercase. Pretty exciting. All right, so now if I call better trace function, uppercase equals true, well, better trace function is a name that resolves to that thing. I call it with uppercase equal false, and what I get back is, I get back trace function, which is this function with this part already bound in, that branch in the code, kind of, because I have that value for uppercase. Okay, so I call that, and I call it with uppercase equal true, right? So here's how I use it. Uppercase equals false, uppercase equal true. In both cases, it's returning the same function, but in one case, it's got a value that was passed in and was part of the closure that was true. In the other case, it was false. Okay, so it's several levels of functions, returning functions, and that's what's confusing about it. Can you write a decorator that can take no parameters? So this is not a function that was called with no parameters. This is just a name of a function. Can you write a decorator that can be used with no call at all or not? Yes, you can. I'm not going into that. It's kind of tricky. There are a couple ways to do that. Okay. All right, so how about this? What's this going to do? Let's create this function you've probably never seen before called return spam. It takes a function and tells you about it. Another close? Yes. Thank you. What are we doing there? Okay. Sorry. I just changed this beforehand. Nope. Paren, curly brace. I can't see other. Why I keep looking over there? Sorry about that. And now I have. Okay. So now I've got this function that just returns spam, the string. Now if I put that as a decorator in front of add, let's decorate add with that decorator. And similar to before, I want you to figure out what is add going to be. Same as the class metaclass. Remember the return spam metaclass, right? So what's going to happen is that the function object that the def add compiles to is passed off to return spam, and whatever it returns is what the name add gets bound to in the current namespace. Right? So kind of silly code, but if you understand what that does, then that, again, you understand that space. Oh yeah, now I know the mechanics of how decorators work. Then that part of decorators shouldn't be scary anymore. And this is just the other way you could have done the same thing. Okay. You can use decorators on classes. They do the same thing, right? Instead of taking the function object that the def created and passing it off to the decorator and using what it returned, you take the class object. You take the class object that Python created and pass it off to the decorator, and whatever it returns is what gets put into the current namespace, right? So you can write, so decorators can work on classes, they can work on functions, okay? And of course, you know what this is gonna do. It's gonna throw the same error, that's right. I'm not even gonna go, you guys can fix it, right? So it's gonna do the same thing, so we'll skip that. Weird class not defined, oh no. Oh, right, because it was interesting. I'm not going to figure that out until later. Okay, so we've covered a whole bunch of name bindings. The only ones I think we haven't covered are when you do a for loop, it creates a name, with creates a name, SADder we did cover, I can't think of any others. I think we've covered all the name binding operations. All right, special methods of classes. So if you are writing your own class and you want it to do something crazy, like have magic attributes that just appear when you want them or whatever, getAttr, getAttribute, setAttr, and delAttr you can use. I'm not going to cover descriptors, get, set, and delete. I'm not going to cover dir. I mentioned it briefly. I'm not going to cover del, but it's just delete the attribute. It's not a namespace operation, so it's sort of like the del statement at the top level namespace. But let me show you an example of how you could use these things. And I've used these a few times to do stuff that would have been just really long and laborious, tons of if statements, and I've used this to create libraries that are really useful for users. I'm saying that just because I think this is a much more likely thing. You're more likely to use this to create really useful code than decorators and metaclasses probably. Well, that's been my experience. Anyway, so what I'm going to do is uppercase attributes. So this is going to be a pretty simple class because all it does is it defines Dunderdict. So if, let me just walk through it and then you'll, so I've created it. I create one of these instances. I look at its Dunderdict. I set that value. I access that value. Dict is there. At this line is where my code takes effect. There is no capitalized attribute 1 in Dunderdict. So this should throw an attribute error. But when Python executes the code, when it figures out there's no such attribute, instead of raising the attribute error, it goes and checks for Dunderdict. And if it exists on this object, then it calls this code instead. Okay, so getAttr is called when there would have been an attribute error. And so what I do here is I take, and it takes 2 arguments, self, of course, because it's a method, it has to take the object itself, and then it takes the name of that attribute. And all I do is I check, is it uppercase? Well, it is. Attribute 1, I put it all in uppercase. If it's not, then it raises an attribute error. You have to do that for it to work correctly, because you want to raise an attribute error if there really isn't one at some point. But if it is uppercase, and if the lowercase version of it's in the Dunderdict, then it's going to lowercase the name to lowercase attribute, and then pull it out of the dictionary, and then uppercase the contents of it. Right? So I don't have an attribute all uppercase, but I can pretend I do, and it just works. Right? And let's test to make sure that yes, we did correctly implement our Dunderdict to make sure that it raises attribute error when it should. Okay? Use cases for this, I used it to do, we had hundreds of files that were all documented in terms of what their offsets, it was flat file format coming from mainframe style stuff. And we wanted to access those by the names of the fields, client number, social insurance number, that kind of stuff. Well, so instead of writing lots of code for every one of these, we just crawled the documentation, spat out something that did something roughly like this. Worked really well. Another one is a company I was helping that was using names in Python are case sensitive, names in the database were not, and at the level they were using it, and so they wanted to be able to handle mixed case between Python and their database correctly. Or correctly was kind of a complicated way. Okay, properties. Cover this briefly. Any questions? Okay. Properties. So this comment here, you might be able to infer what's going on with setter and deleter attributes. So a property is, in Python, is the way you can add behavior for specific attributes. Okay, so if you want, a great toy example is if you want to, points can be a point on a graph, on a Cartesian plane, can be in polar coordinates or Cartesian coordinates, and you can interchange between them. Well, maybe you want to make a point class that the user can either set or get them in either format. Well, you could do that with properties and only store them in one format behind the scenes. Toy example, but there are other examples that hopefully you can imagine. Like I said near the early part of the course, I'm not going to give you an authentic case here, an authentic example. But what we do with this is I'm just going to start by creating this underscore x, and then I'm going to put this decorator in front of this class, in front of this function, which is effectively a method because it's inside a class, right? And the name X is going to be bound to a name in this namespace, i.e. is going to be added to that dictionary that gets passed off to the type function. But what's going to be added to it is going to take this code object, pass it off to that decorator, and what that decorator returns is what is going to get to be the value of that key value pair X function object. Okay, so it's kind of weird because we're using decorator inside a class to think about those two mixed together. Anyway, all it's going to do is say, I called it, right? I'm just going to document what's happening. This is kind of cool, is that property decorator returns an object that not only does the right thing for X, but that function has an attribute, which is the setter, and an attribute, which is the deleter, which just makes it kind of nice syntax here. You can create the getter, and then if you want, you can create the setter and the deleter as well. Okay? So how does this work? Well, we just create the property. So if we look at underscore X. So p.x, so you can see it called that. So that means up here, I could do whatever I want. I could set it to something else. I could switch from polar to Cartesian. I could double it. I could, log that it got set. I could audit, have a trail of when it got set, all sorts of stuff. And same thing for the getter and the setter. Oh, I did that one. Oh, I don't know the getter, sorry. There's the setter. And the deleter, again, which isn't deleting the object, it's deleting the name, the attribute. Okay. So people who learned in Java always use getters and setters. Don't name in Python, you can add them later. That's the short version. Here's another example of a get adder, which I'm going to skip, I think. No, I'll go through it quickly. So here's what I want, if I have a release that looks like, one of those lines, I want to be able to get pieces out of it. And this is just a demonstration, a simple version of what I was telling you earlier. So I can set a property name and a property version and a property date, which just returns the attributes, the offsets in that string that I want. So now I can say, there's my release pulled out of that list, and I can create one of these objects, and then I can access elements, right? I can say release name, version, date. So this object here wraps this data, or actually just one line of this data, into a friendlier format that just has the names, right? So sort of like I was telling you I did with those hundreds of file formats. Except we used this for it. We used this instead. We use something like this. We define the slices ahead of time, and these we actually generated from documentation. And then I used getAdder. And again, this looks, that's interesting. That ain't gonna work. I don't edit this directly. I edit it in a different format and then generate the IPython notebooks. So that's what happened here. Something must have gone wrong there. Right, so I used those slice objects before, and I just say, well, when they ask for an attribute that doesn't exist, and the only one that does is .data, then it checks to see if it's one of these names, and if so, it pulls that piece out. See, this can even work with my, it does. And of course, let's make sure we did it right. Yep. Nope. I got our name. I got an error in my, I have another typo in there. Attribute. I changed this to attribute. So, so it failed for another reason. Nine minutes. I'm going to keep going. I'll just show you what this does, or you can play with it later. I'll just let you play with it later. This one as well, just sort of plays with what these things do. I'm going to move on to a simple example here. And I'm not going to get to, I said I wouldn't get to the last two sections. Well, I'll get to this one, but not quite the one with iterators. I'll let you do that on your own. I know ahead of time I'm probably not gonna, but sometimes I get further along and figure I'll give you that to play with on your own. You'll learn something there if you want. Okay, so I want to create a little calculator so that those 4 assert statements in a test would work. So it's a pretty simple calculator. It only takes 3 characters, but it shows you what I want to show you. So you can do assignment in Python, like left-hand side operator, right-hand side equal, and as long as it's an iterable on the right side that has the same number of elements as the left-hand side, it'll assign those 3 names. All right, so there they are. I'm going to convert 2 of them to ints. And then here's the sort of straightforward way to write this code. I define that function that just checks to see what operator it is and calls the various functions. And I can call that function and it will work. But it has a lot of boilerplate, a lot of duplication here. If, op, equal, equal, and then the only thing that changes is right there and right there. All the rest is the same. So I'm going to instead use the operator module, which has names for all, names of functions that do what the operators do. They're all in there, right? So now I can create a dictionary. So some of you are looking at this going, yeah, this is obvious. But some of you are going, I would never would have thought to do that. And the reason you never thought of doing it this way is because you've been trained by the language you've been using, or the languages you've been using for a while. So especially if you're new to Python, coming out of Java, for example, you go, I can't do that anyway. But in Python, you can do these kinds of things. The line between code and data is much blurrier in Python, and you'll often find people stuff into data what would have been put into code in other languages. So here's my mapping. And I can access an element of it, and I get back the function object, which itself is callable. Right? So I can actually call it. I get that object back and call it with 7.3. I should get 10. And it works. So now my perform operation just turns into that one line, which uses this data structure. So you could do a lookup using a hash table. All right. And so here's my calculator. Just combine that code together. Calc 7.3, Calc 9.3, everything works. Except for that one, because it doesn't work. And again, this is a toy example. Why would I do this way? Well, the answer is if you have lots, if you have hundreds of things you're trying to do, and it's all coming from a spreadsheet you already have or something like that, well, that's when this one shines. In this case, it's kind of made up. I forgot the slash. The way I change my code is I add to the data structure, and suddenly my error goes away. I've extended my code by using that. Okay? The Dunder call method is a method you can add to a class, which makes instances callables. Let me show you how it works. Right, so I'm going to create an instance of the sentence ends with class, passing it dot, which will get saved as punctuation, and it's just going to use that to see if the last character in whatever I pass to this thing is in that. So I have ends with dot, true, ends with dot, no. Right, so you can see that ends with dot is an instance of this class, but I can call it. So when Python sees, when it tries to call something, an object, before it gives up saying it's not a function, it's not a class, it says, well, does it have a Dunder call method? And if it has a Dunder call method, it'll call that instead. Okay, so that's kind of handy, and you can see that it just does what you expect. and I will let you do that on your own. I think we'll end 3 minutes early. Please, please, please fill out the survey, which is somewhere here. There's the survey link. Okay, thanks for coming. Feel free to stay after, ask questions. Give me feedback in terms of, Stuart, that didn't work there. Stuart, that was great, whatever. Especially the stuff that's corrections, I like to keep improving. Okay.